Earth's oceans are rising, and space lasers just proved why for decades satellites have quietly fired laser pulses across space, measuring Earth with extraordinary precision. Now, those measurements have revealed a stark conclusion. Global oceans are rising not just steadily, but at an accelerating pace, driven increasingly by melting land ice. If you like my videos, subscribe my channel and press the bell icon to turn notifications on, so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. A comprehensive 30-year analysis spanning 1993 to 2022 shows that global mean sea level has climbed by roughly 90 millimeters, about 9 centimeters, in just 3 decades. On average, sea levels rose approximately 3.3 millimeters per year, and crucially, that rate is increasing. The message is clear. The mechanisms driving sea level rise are intensifying. Sea levels increase for 2 fundamental reasons. First, seawater expands as it warms, and the oceans absorb nearly 90% of the excess heat trapped by greenhouse gases. Second, water from melting land ice glaciers and ice sheets flows into the oceans, increasing their total mass. While thermal expansion dominated earlier discussions, this new research shows that the balance has shifted. Today, added water mass from melting ice has become the leading driver of sea level rise. What makes this study particularly powerful is how the scientists measured that mass increase. Instead of relying solely on satellite altimetry, which tracks ocean surface height, they used time-variable gravity data derived from satellite laser ranging, SRR. This technique involves firing laser pulses between satellites and ground stations to measure tiny variations in Earth's gravitational field. Because gravity subtly changes as mass redistributes across the planet, researchers can detect when oceans gain water. Historically, SER faced technical challenges: limited satellite coverage, high orbital altitudes, and relatively coarse spatial resolution. To overcome this, the team developed an innovative, forward modeling method that incorporates detailed land-ocean boundaries, dramatically improving the technique's precision. This breakthrough allowed them to reconstruct the first direct 30-year record of global ocean mass change, extending nearly a decade before dedicated gravity missions began in 2002. Their findings are striking. About 60% of the total sea level rise since 1993 resulted from increasing ocean mass rather than warming expansion alone. Since around 2005, melting land ice has become the dominant contributor. Over the full 3-decade period, more than 80% of the added ocean mass came from the loss of polar ice sheets, particularly Greenland and mountain glaciers worldwide. The implications extend far beyond measurement. By independently confirming how much ice melt contributes to sea level rise, the study strengthens confidence in climate models used to forecast future coastal risk. It also highlights a troubling trend. As global temperatures climb, land ice loss accelerates, and with it, the rate at which oceans rise. In essence, space-based lasers have given us a new way to weigh the oceans. And what they show is not just gradual change, but momentum. The oceans are rising higher, faster, and increasingly under the influence of melting ice from a warming world. The material system iron telluride selenide is particularly intriguing because it naturally combines 3 ingredients required for topological superconductivity: intrinsic superconductivity, strong spin-orbit coupling, and significant electronic correlations. Previously, these properties were explored in bulk crystals. However, bulk samples suffer from chemical inhomogeneity and are difficult to integrate into practical devices. The new work instead focuses on epitaxial ultra-thin films, which offer superior uniformity and compatibility with semiconductor-style fabrication. This thin film approach is more than a convenience, it is a technological advantage. The films operate at temperatures up to about 13 Kelvin, substantially higher than many competing platforms that require cooling near 1 Kelvin. That difference may seem small, but in quantum hardware it translates to dramatically simpler and more scalable cryogenic systems. Moreover, thin films can be patterned and structured with precision, enabling direct integration into prototype quantum circuits. Conceptually, the advance reframes how researchers approach topological superconductors. Rather than searching for rare materials that accidentally exhibit the right properties, scientists can now engineer the phase diagram itself through controlled chemical design. A fractional change in elemental composition becomes a quantum phase, dial shifting the system from ordinary superconductivity into a protected topological regime. If scalable quantum computers are to become reality, they will require qubits that resist environmental noise without constant error correction. By showing that topological superconductivity can be chemically tuned in a controllable thin-film platform, this research provides a practical pathway toward that goal. Sometimes, progress in quantum technology does not come from adding complexity, but from adjusting the recipe with extraordinary